Have you ever just stood there looking at some crazy complex factory machine, or even just the suspension on your car, and wondered how all those moving parts actually work together without, completely tearing themselves apart? Well, you are in the right place. Welcome to this explainer. Today, we're going to take a sort of anatomical journey into the hidden skeleton of joints, links, and gears that power our modern world. We're going to decode the fundamental world of mechanisms.
Okay, let's take a really quick look at our roadmap for today. We'll be covering the blueprint of motion, calculating freedom to move, dimensions and motion characteristics, Grashoff's law of rotation, the magic of inversion, and finally, maximizing mechanical advantage. Let's just jump right in, shall we?
So part 1, the blueprint of motion.
To really get what we're studying today, we need to chop the massive science of mechanics into a couple of camps. First, you've got statics, which is all about stationary stuff where time just isn't a factor. And then there's dynamics, where things are actually moving and changing over time. But dynamics actually splits again. For this explainer, we are zeroing in strictly on kinematics. That's the pure geometry of motion. We're talking positions, velocities, and accelerations, and we are completely ignoring the actual forces or kinetics for now. Oh, and to make the math work, we're going to assume all the parts we're looking at are perfectly rigid. No bending, no flexing under pressure.
Keeping that rigid assumption in mind, what are we actually building? Look, if you just bolt a bunch of rigid links together, you get a structure. Think of a bicycle frame welded from steel tubes. Nothing moves. But if you take a closed chain of those links and bolt exactly one of them to the ground to act as a frame, boom, you have a mechanism. Its whole purpose is transforming motion. Sort of like a mechanical waving hand in a storefront window. Now, if that mechanism also transmits power to do actual useful work, that's a machine, like the gas engine sitting inside your car.
Now, when we connect these rigid links, we use what are called kinematic pairs, or just joints. Think of these as the fundamental cells of our mechanisms. We categorize them by their degrees of freedom, or DOF. A revolute joint, like a basic door hinge, has exactly 1 degree of freedom, pure rotation. But a spherical joint, like the ball and socket in your shoulder or a car's suspension, gives you 3 degrees of freedom. And honestly, the specific joints you pick will completely dictate how your mechanism eventually moves.
Moving right along to part 2, calculating freedom to move.
So, once we start snapping all these joints together to build our moving skeleton, we really need to know how much control we have over the whole system. If you look at a huge, complex factory robot with multiple arms, you might wonder, how many motors do you actually need to drive that thing? Slap too many on, and they'll literally fight each other. Put too few, and the arm just flops around uncontrollably. Luckily, math gives us a totally definitive answer to this.
Enter the Kutzbach criterion. It sounds a bit intimidating, but it's crucial. By counting up your total number of links, that's n, and yes, you have to include the fixed ground link, and then tallying up your 1 degree and 2 degree of freedom joints, you can calculate m, the mobility. If m equals 1, your mechanism needs exactly 1 independent input, like a single motor, to have perfectly predictable motion. If it spits out a 0, well, you've accidentally built a locked-up structure.
All right, part 3, dimensions and motion characteristics. So most of the mechanisms you see every single day are what we call planar mechanisms. They're everywhere because honestly, they're just way easier to visualize, manufacture, and do the math on. Every single point on the mechanism moves in parallel 2D planes. You could trace their whole motion on a flat piece of paper. Spatial mechanisms, on the other hand, throw those rules out the window. They allow for wild, unrestricted, 3D movement. The calculations are a nightmare, but they are absolutely essential for advanced robotics where motion just can't be confined to a flat plane.
Next up, part 4, Grashoff's law of rotation. Okay, say we want to attach a continuously spinning motor to one of those common flat linkages. Motors turn in a full 360-degree circle, right? They don't just stop and reverse mid-cycle. This is where Grashoff's law comes into play. It dictates whether at least one link in a 4-bar mechanism can do a full spin without jamming everything up. It's super simple. Take the length of your shortest link, S, and add it to the longest link, L. If that total is less than or equal to the remaining 2 links, congratulations, you've got a Grashoff linkage, meaning at least one part can spin all the way around.
But here's where it gets really interesting. Just because a link can spin doesn't mean the machine behaves the way you want it to. It all depends on which link you decide to bolt down to the floor as your frame. If you fix the link right next to your shortest one, you get a crank rocker. The short link spins, and the output link just rocks back and forth, kind of like a windshield wiper. But if you bolt down the shortest link itself, now you've got a drag link, where both the side links spin in full circles.
Which brings us nicely to part 5,
the magic of inversion.
Speaking of choosing different ground links, this concept right here, kinematic inversion, is honestly mind-blowing. It shows how shifting our perspective changes absolutely everything. Let's look at a standard slider crank. You've got a frame, a crank, a connecting rod, and a sliding piston. Historically, by just changing which of those 4 pieces was anchored to the ground, engineers invented 4 totally different machines. If you fix the cylinder block, you get your standard car engine. Fix the crank instead, that gave us the rotary engines used in early airplanes. Fix the connecting rod, and you're driving a steam locomotive. Fix the piston, and you've just built a garden water pump. One single skeleton, 4 completely incredible applications.
Finally, part 6, maximizing mechanical advantage.
Let's talk about the real muscle of a machine, power and force. I mean, the whole point of building these things is to multiply force, right? Mechanical advantage tells us exactly how much output force we get for our input effort. But here's the catch. Because these linkages are constantly moving, this isn't some fixed number like you'd get from a basic seesaw. The mechanical advantage is actually fluctuating wildly, depending on the exact geometry and angles of the links at any given millisecond during the cycle.
And here is a real game changer. When the input angle between your driver and the coupler hits exactly 0 or 180 degrees, the mechanism enters what we call a toggle posture. At that precise split-second moment, the mathematical equation for mechanical advantage literally hits infinity. Basically, a tiny amount of input torque gives you a massive crushing amount of output force. This geometric trick is exactly what engineers use for heavy-duty clamping tools or rock crushers.
But we do need a quick engineering sanity check to keep us grounded here. We have to watch the transmission angle. That's the angle actually transferring the force onto the output link. If that angle dips below 40 degrees, the physics of friction completely take over. I don't care what your pure kinematic math says, in the real world, that mechanism is going to bind up and lock on you. So, we've covered the foundational cells, the mobility math, and the forces of these linkages. But I want to leave you with a bit of a provocative question. Are these strict mathematical rules, like the Kutzbach criterion we looked at earlier, always 100% right? Well, spatial anomalies, like the famous Bennett linkage, prove that sometimes Kutzbach calculates that you have a rigid, locked structure, but because of some very special, twisted 3D geometry, the thing actually moves anyway. It just goes to show that while the blueprint of motion gives us amazing predictive power, the physical world always has a few rule-breaking surprises waiting for us. Really makes you want to dive into advanced spatial kinematics next, doesn't it? Anyway, thanks for hanging out for this explainer, and next time you're out, take a closer look at all the machines moving around you.